calculus class. We are going to start chapter 6, and this is section 6-1. The title of chapter 6, by the way, is Applications of Integration. So in chapter 5, you learned all about how to evaluate both definite and indefinite integrals, and this is an applications chapter. So in 6-1, the application is very simple. I hope you can read it up there. It says area between curves. Okay, so, we know that a definite integral represents an area. A definite integral represents an area between a curve and the x-axis. We're going to apply that concept to be able to find the area of regions that aren't necessarily bounded on one side by the x-axis. So I've got a region drawn up here. A region, I'm pointing to it right here. This region is bounded, okay, this region right in here. It's bounded above by the curve f of x. It's bounded below by the curve g of x, and it's bounded on the left there by the y-axis. Okay, so it's not a triangle, but it's it's a region that has three sides. Okay, they're not all. Two of them, I guess, are linear, but that f of x is a curve. So we're going to use kind of the concept of integration here. Probably the simplest way to think about this is I know how to find the area between the curve g of x and the x-axis. I can do that with a definite integral. I know how to find the area between the curve f of x and the x-axis. That can also be done by a definite integral. Since I want just this area right here, if I, and let's say that these two curves intersect at the point x equals a. If I just do the integral from 0 to a of f of x dx, that's going to get all the area beneath that curve f of x and the x-axis. That's going to be too much area, right? That's more area than is shaded. So what I have to do is I have to take away that area that's below the line g of x. Well, the area below the line g of x is represented by the integral from 0 to a of g of x dx. So here's the area beneath the curve f of x from 0 to a. Here's the area between the curve g of x from 0 to a. And if you look at it, what I really need to do is take that entire area under the curve f of x, and then I need to subtract away the area that's between g of x and the x-axis. So I'm simply going to take this area minus this area, which should give me the area of the shaded region. Now, I can simplify this expression just a little bit. If you notice, this is the integral from 0 to a of one function minus the integral from 0 to a of another function. I can rewrite that as one definite integral. That's just the integral from 0 to a of f of x minus g of x dx. And this is essentially a formula that we can use then to find the area between two curves. Okay, that's the area between two curves, and this is how we find it. Now, that's one example, and I didn't put any functions with it or anything. Let's look at something else a minute here. Okay, this whiteboard is not quite as good as the ones that I am used to at school. Of course, the eraser has some stuff on it. Fix that. Sorry. What I have to show you is a case where the boundary functions are functions of y rather than functions of x. So I'm going to draw a second region here. And this time I'm going to make a parabola open sideways degrees. And then let's make a line go like this. Okay, so we'll call this parabola. Now, this is a function of y, okay? Notice it passes the horizontal line test. It's not a function of x. It doesn't pass the vertical line test. So I'm going to write this as f of y. Okay, so the rule for this might be x equals like f of x is the same as y equals something. Well, f of y is the same as x equals some expression in y. Okay, and then we'll call this line. This will be g of y. Okay. All right. Now the region in question here that we're going to try to find the area of is right here. Okay, and if you notice, this doesn't have a consistent upper boundary. If you notice, the upper boundary of this region is given by g of x here, but then over here it looks like it's g of y, but it's given by f of y there for a little bit. So this is going to be easiest if I integrate with respect to y. Now, here's something you got to look at here. Okay, the area between f of y and the y-axis is given by the integral from here to here of f of y. Okay, the area between g of y and the y-axis is given by the integral from here to here of g of y. Okay, so the area of the shaded region then is going to be, and okay, this is going to be the point where y is a, and this right here will be the point where y is b. We always integrate from least to greatest, from low to high, just like we do when we're integrating with respect to x. So this area right here can be given by the integral of the integral from a to b of f of y minus g of y dy. Okay, just like when we were integrating with respect to x, when we were finding an area where we had to integrate with respect to x, we always integrated the top curve minus the bottom curve. Okay, when we're integrating with respect to y to try to find an area between two curves, we integrate the rightmost curve minus the leftmost curve. Okay, listen, I want you to try a few of the 6-1 problems. Okay, and you can email me with questions if you have one of the problems that you'd like me to work out for you, either as a picture or a video. You can let me know on that. Please let me know how you're doing. Good luck and stay safe.